So I'd finished with what's the pattern? Will there be more elements? Only at the very, very bottom. We can keep going with 121 and 122 and 100. We can, in fact, we are doing those in particle accelerators, but there will not be any more elements up in the upper section. We found everything. Atomic mass. This is the average mass of an atom. And that's why if you look at your pink periodic table, you'll see a lot of the atomic masses are decimals. Because Mr. Dueck, you said that protons, you didn't come in decimals. It turns out, Brooke, try that again. Sometimes the number of neutrons can change in a nucleus, especially for radioactive stuff. And so that atomic mass is an average mass. It's saying, well, most of the time you have this many neutrons. Sometimes you only have this many neutrons. Here's the average. What we do is we always round off properly to the nearest whole number if we're going to use the atomic mass in our head. So the number of protons never changes. So how could the masses of two atoms of the same element be different? What else can change? I gave you, in fact, I mentioned it about 30 seconds ago. What can change that has mass? Neutrons. And zeros can change, especially for stuff that's radioactive. So the atomic mass is the sum of the protons and the neutrons in the nucleus. And because this number can change, this number is a decimal on your periodic table often. It's not a nice whole number. What's the pattern? If you look at your pink periodic table, as you move to the right, what can you say about the atomic masses? There is one and only one exception. See if you can find it. There's a candy to the first person who can find on their periodic table the one spot where suddenly when you move to the right, oh, it got smaller. I'll pause for a second. So what's the pattern? Generally, it increases from smaller to larger. Okay. With one exception, but there's going to be exceptions to almost every rule that I give you, Christian, but we're going to call them rules and say, for the most part, they work. Ion charge. It turns out, and this is the secret to figuring out how everything is formed, atoms can gain or lose electrons, because those are in those outer shells, which means they're more accessible. And when they do, they become charged, because you now have more positives than negatives, or more negatives than positives. We say that's charged. If you've ever seen static electricity, what we're really saying then is they'll cling or they'll combine with other stuff. When an atom doesn't have the same number of electrons as protons, we call it an ion. We say they're forming ions. If you gain electrons, now who remembers from the last unit, electrons, what was the charge on an electron, positive or negative? Okay, so if you gain negatives, you become even more negative. And this is tricky, Brooke, because people want to think, well, you've just added something. Shouldn't it be more positive? But you've added negatives. So it's going to be more negative. But it's easy to get that mixed up. If you lose electrons, become positive. I've told the joke already, right? Atom walks into a bar, says to the bartender, I've lost an electron. The bartender says, are you sure? The atom says, yes, I'm positive. There's the punchline. And then I wrote here, what's the pattern? So if I look at my periodic table, this number here is the ion charge. What do you notice about the ion charges of the metals on the left side of the periodic table? What can you see? What can you tell me? They are all what? Positive. Metals want to lose electrons, which is why they conduct electricity so well. What can you tell me about the non-metals, these ones in this section here? They desperately want to gain electrons. And in fact, that's one of the reasons some of these are so toxic. For example, chlorine gas wants to gain electrons so much that if you breathe it or if it touches your skin, it will literally rip the electrons from the molecules in your skin. We call that burning bad. Okay? What can you tell me about everything in this right-hand column here? What's their ion charge? We call these the inert gases, and the reason is they basically don't want to combine with anything. When I was in high school, I was taught they don't combine with anything, but actually a guy at UBC managed to get one of them through a clever experiment to force it to combine with something. So now, again, there's an exception to every rule. I'll say they really are, they almost never combine with anything. Okay? So what's the pattern? Metals become positive, which means they lose electrons. And again, this is tricky, Brian, because people want to think, well, if you're losing, isn't that smaller? Isn't that negative? It's because electrons are negative to begin with. When you lose negatives, you become positive. This is like that whole minus minus is a plus that you learn in integers. Non-metals become negative. They want to gain electrons. In the middle, those weird metalloids that I told you about, well, in the middle, some form more than one type of ion. So if you look in the middle of your periodic table, like right here, you'll see, for example, chromium. It's happy losing 3 electrons. It's also happy losing 2 electrons. It's most happy losing 3, but there are some situations where it'll be okay losing 2. These ones are nice, but you can see when you get to the middle, you get what are called multivalent charges. We'll talk about what that means. Multivalent atoms. It says worksheet, first section, page 28. We're going to come back to that. Let's keep going. I forgot to include this in your notes. Sorry, but I think you have room at the bottom of the page. Sorry. So you need to write this down. Sorry. Here's another rule. Basically, the further down... Did I include this in your notes? I don't think I did I? No. So you have room at the bottom of that front page. There's like a long little strip at the bottom, yeah? Here's what it says. The further down you move and the more further out you move, the more chemically reactive an element will be. Rule. The further out and the further down you move, I've been down and out. No. The further down and out you move on the table, the more chemically reactive the element will be. So we're going to do some questions. Don't write these next 3 down just yet. We'll answer them first, and then you can write down. Potassium is more or less than reactive than lithium. Is more or less reactive than lithium. On your pink periodic table, find potassium, find lithium. Lithium is element number what? 3, see it? Potassium is element number what? 19? Okay, to go from lithium to potassium, are you moving down or are you moving? Okay, so you know what? More reactive. As you move down, it's more reactive. What about magnesium, Mg, and sodium, Na? What element number is magnesium? Element number what? 12. I'll put a little 12 here. What element number is sodium? 11. So the rule is as you move down, it's more reactive. As you move out, it's more reactive. So what do you think? Is magnesium more or less reactive? Less, because it's closer to the middle. What about S sulfur, which I think is element number 15, 16, something like that, I think. What number is sulfur? 16? And what number is chlorine? 17? Sulfur, is it more or less reactive than chlorine? Less. Okay. I like that question. I like that question. I like that question. Why would I say that? You know what? That might make a nice little, like a true false or a little multiple choice question, right? Sorry, I forgot to include it in your notes, though. And I forgot last year and this year, so next year I'll try to remember. You okay with that? People are still writing. I'll wait. Families. Hey, families. So vertical columns on the periodic table have similar properties. We say they're all part of the same family. Turns out there's a total of 1, 2, 3, 4, 18 families. You don't need to know all 18, but there's a few that you're going to want to know. The left column of the periodic table, and I think it's actually on your periodic table, the name for that column. What do we call the left-hand side? These are called the alkali metals. They're very reactive, they're very soft, and once you've written down the word alkali, you can put your pencils down and look up. The second type is column number 2 from the left, which I think is also labeled on your periodic table. These are called it's almost spelled the same way, except I think there's an N, alkaline earth metals. Alkaline earth metals. These are actually cool because it turns out if you apply enough heat, they'll burn in air, and they burn with bright colors. In fact, they are used to make fireworks, along with some of the alkali metals and some other ones as well. But these are often used in fireworks. Put your pencils down. So the first family I said, Caitlin, that was worth noting was alkali, column 1. Then alkaline metals, column 2. Another very important family is family number 17, the 17th column. What are those called? I think it's on your pink periodic table, is it not? Halogens. These are very, very reactive. To the point where most of them will burn your skin. They're so reactive. They'll rip electrons from your skin. In fact, all of them will. Okay? Put your pencils down. Short video. And pick up pencils. So, you're going to need to know 4 families. The first one was the alkali metals, far left. Second one was second in from the left, the alkaline metals. Third one is second in from the right. Fourth one is far right. In other words, the 2 outer rows on either end, those are the ones that you're going to have to become familiar with. So we have the very last one is called the noble gases. The last column. These are very non-reactive, which is why they used to be they're called noble gases. The idea was, oh, they're so noble, they're so nice that nothing can make them mad or angry. They never react to anything. They just stay all calm and I'm very noble. Yeah. Okay. We used to say, Carter, that they didn't react with anything at all, and for the longest time it was thought they wouldn't react with anything. And then I think I told you, I think in 1973, a prof at UBC managed to get either xenon or radon to react with something in it. Holy smokes, you can do it, but you really need to force it and add lots of energy. It's very difficult to do. Oh, I got a video there. Put your pencils down. The noble gases. Note, I wrote here that periods or rows go across the periodic table So we say that there's period 1, period 2, period 3, period 4, and that's going sideways. And families or groups go up and down vertically. So bromine, on your pink periodic table, can you find bromine, please? Bromine, find it. What element number is it? Okay, you got it? It's in period what? Count down what row it's in from the top. Careful, I don't think it's 3. Isn't it 4? Because the 2 ones at the top make a row. So, ready? Let's go find it, Mr. Dueck. Row 1, row 2, row 3, row 4. It's in period 4. Nice yawn, Brooke. And row number, the nice thing is the row numbers are all labeled along the top there. Row number what? 17. And family, what do we name that family? Halogens. Helium is in period what? 1. And row 1. Oh, hang on. You know what, Mr. Dueck? I totally botched this. Scribble that out, guys. It's in period 4 and row 4 and family 17. That's what I meant to write. Good gosh. Because periods and rows are the same thing. I said period row 4, row 4, column or family 17. Period 1, row 1, family number, helium is in family number 18, which is the noble gases. Put your pencils down.